So he had this idea of this, what we now call Dyson spheres, where a civilization could build something so large that it will actually block part of the light from the star and radiate in the infrared.
Right.
So I think this was the first proposal of a technosignature that was not a radio signal.
Episode 107, SETI's new tool, Technosignatures. The Great Wall of China can be seen from space. Actually, it can't, but the idea that a civilization could build something large on a planetary scale that could be detected from interstellar distances was articulated first by author Olaf Stapledon in 1937 and popularized by Freeman Dyson in the 1960s. Known today as a Dyson sphere, it's a megastructure built by an alien intelligence that captures almost all the energy emitted by its star. In this episode, Dr. Hector Socas Navarro explains we humans are not there yet, but the increasing density of Earth's geosynchronous orbit will become detectable in a couple of centuries. So not a Dyson sphere, but a ring or a belt he calls the Clark exobelt, may allow alien civilizations to detect humanity's presence over interstellar distances. In this episode, we discuss the opportunities for SETI to detect artificial structures like this at interstellar distances using the James Webb Space Telescope and the very large Earth-based telescopes coming online soon. Links to the resources we discuss are on this episode's page on the website. I started off our conversation by asking him about Tenerife in the Canaries, where he's based.
It's really amazing because this island, the landscape changes so quickly. You drive around for half an hour and you feel like you're in a whole different country. And in particular, going from sea level, where most of the towns are, and you drive up the mountain, and in just 1 hour, you are, even above the tree line, above the clouds, and in this absolutely magic landscape that looks like from another planet. It's really amazing, yeah.
And for astronomers, I've always known about Mount Teide and the number of observatories you have there, which is one of the many things I could talk to you about. But I do want to talk to you about your interest in the search for extraterrestrial intelligence. But you studied astrophysics. How did you get into SETI in the first place?
Well, I would say it's just a matter of personal interest. I have always been interested in the idea of life elsewhere in the universe, and especially intelligence. I think that's probably something we all share. It's very human-like to ask these questions about other forms of life, other beings that we could communicate with. And myself, I think I was very profoundly influenced by Carl Sagan when I was growing up as a child. I watched Cosmos. I read the book. I read everything that would fall in my hands written by Carl Sagan.
Right.
And he was very interested in all these subjects, and he was able to discuss them in such a beautiful way, but at the same time in such profound and scientifically rigorous way that it really, I think that has always been with me. And when I decided to become a scientist, of course, I wasn't really thinking that I would be working on these fields in particular, because, when I was growing up in the 80s, the 90s, SETI was not a popular research topic. I would say it still isn't, but back then it was something considered almost hopeless. If there's someone out there, it will be so far away that there's no, it will be virtually impossible that we could make any kind of contact.
Mhm.
But now, things have changed a little bit, and now there's a growing interest in this field, and I couldn't help but try to sneak a little bit into this field, which I find so fascinating.
And you're quite right about the deep impact on the futures of so many lives, including mine, that the work of Carl Sagan and his many books, including Cosmos and particularly Contact and the film that went with it, there's a whole generation of, I think, working scientists and engineers today who can probably trace their roots back to his work. And I'm sure every generation has its own origin story like that. But you're quite right, and it's something that I share. Just as an aside, I'm very interested in people. I think you're a bit of a musician. You do a podcast, and you're a director of the Museum of Science and Cosmos. Tell us a little bit about all three.
Well, I wouldn't call myself a musician by any stretch of the imagination.
Right.
But I am interested. It's something that interests me, but I've never had enough time in my life to devote to what I would really like to learn, which is about composing music, music composition. That's a subject I find fascinating, and I've read a little bit about it. And when I was young, I learned a little bit to play the piano and electronic keyboards, just enough so that later, with a little bit of help from technology, I could play around and put things together. And I do not want to say create, but you know what I mean.
Just I think you can say create. So I think of you as a musician, somebody who doesn't do anything like that. So behind you, I can see a poster, Coffee Break. Tell us about Coffee Break.
Yes, Coffee Break is a podcast that we make, me with some other friends and colleagues. We started doing it 7 years ago in 2015. And it's peculiar in a bunch of ways. First of all, we wanted to talk about the news in science. So this is not a podcast that you would tune to learn something very basic about, how stars are formed. Instead, it's something that we make every week, and we talk about the latest papers that have come out, or some other news that are out there. So it's more for people who are interested in keeping up to date with what's new in science in general, but especially in astrophysics and physics, which is what we are most interested in. And it's also peculiar in that we try to keep it as genuine as possible, in the sense that it's not scripted, and it's a conversation among friends. So we just sit there and start talking, and sometimes we forget that people are listening, and sometimes we get technical.
Right.
And we've learned, at first I was very worried about this, but we've learned that it's okay, that there's an audience who enjoys this kind of conversations. And sometimes you don't have to sort of explain everything at a very low level so that everybody can understand it. I mean, there's a lot of people who already have a background and they know a lot, and they want something at their level, and there's not a lot of outreach out there for people who already have certain background. So we do not cater to the big public, to the masses. We're not looking for a great audience, but we were surprised to see that there's still a lot of people who are interested in listening to our podcast, just because there's not much like it in that way. That we are not going to break it down to something so simple that anyone can understand it at the expense of lying, basically, because then what you end up talking has nothing to do with the actual story. But.
And then, of course, you as an astrophysicist, as a scientist, the other participants, bit of a panel, they're all scientists, working scientists in this field. So it's quite natural. And it's pity, actually, I can't think of, all the podcasts that exist, there isn't anything that I can think of straight away that deals with sort of science or space-related news on a weekly basis. Now, it is in Spanish, but you do have little bits of it in English as well. Is that right?
Yes, it's in Spanish. It's for the basically our audience is listeners in Spain and Latin America.
Mm-hmm.
Unfortunately, there's not so much content about science and technology in Spanish language as there is
Right.
in English language. So we thought that would be a good market for us. But yeah, sometimes we have like interviews or conversations with other colleagues from other countries, and then we speak in English, which is the universal language. We were talking about this earlier. I really like the idea of having a universal language that all humankind can communicate. I think we need communication, and it's great that we can that the English language can serve this purpose. So sometimes we have these conversations in English with international colleagues and friends. And of course, when we put these conversations in the podcast, we record them in advance, and then we add a voiceover in Spanish so that our audience can follow it. But we also publish the original English audio because a lot of people speak English and they would rather listen to the actual words of our guest rather than a translation, which is never perfectly accurate. So we also publish the English conversation.
You're the director of the Museum of Science and the Cosmos. Great name. Where is it? What do you do? And how long have you been doing it for?
Well, I've been doing it for a little over 3 years now, and it's something completely different from what I was used to doing as a scientist. Is completely different. This is a museum that was built by a partnership between my institution, the Institute of Astrophysics of the Canary Island, in partnership with the local island government, or I should say, it's more like the island government in collaboration with my institute. The institute will provide all the scientific advice, and also the agreement was that one of the scientists from the institute will be the director of the museum.
Right.
So when the previous director finished his term, they asked me if, because I had this profile, I like to do research. I had a podcast which was growing in popularity. So perhaps I would guess that for that reason, they thought I would be a good candidate to be the director of the museum.
So let's move on to the search for extraterrestrial intelligence, or SETI. Now, I'm really interested in speaking to you because you've written a paper quite not recently, but 2016 was it, I think? And there's been a lot of developments in this area. But let's just start off with the background. The SETI search started with Frank Drake in 1960s. Mostly it was radio-based, searching for signals from extraterrestrial sources. And the idea is that if there is a signal, radio signal coming from an extraterrestrial source, there must be, therefore, some intelligent life behind it that's generating it. Can you just summarize where we are right now with the SETI search? I mean, it's radio most of the time. What's going on now? And are you actively involved in any SETI project as well?
Okay, so I think it's a very exciting time now for SETI research, because as you mentioned correctly, this was started by Frank Drake, was one of the pioneers in the 60s. People realized that we have these radio telescopes, and radio communications were becoming increasingly popular on TV and all of that. So it was natural to think that it will be also a good form of communication between stars. And a lot of people started doing something that had, or not a lot of people, but some people started doing something that had not been done before, which was to point these radio telescopes to nearby stars and see if you could pick up a signal from an intelligence trying to communicate with somebody else. And at the time, I mean, it might seem naive now to think that there could be other civilizations out there just sending radio signals, but at the time we didn't know. So and you don't know until you actually go out there and listen and see if there's something. So there were some very brave efforts in the 60s. Frank Drake was one of the pioneers. There were also efforts in the Soviet Union, but we don't know so much about these efforts as we know from the Western counterparts. And yeah, at the time, I think what people could come up with in terms of how we could communicate with other civilizations with existing technology, radio signals was the only thing that could be considered. The only exception was this idea by Freeman Dyson, who was a very famous physicist and very brilliant scientist. He probably should have won a Nobel Prize and was very close. But he was one of these brilliant minds who was interested in many different things. So it's difficult to win a Nobel Prize if you don't focus on one thing and carry on for 30 years doing the same thing. But I really liked Freeman Dyson's way of the way he understood science and how he liked to focus on some problems, try to make some progress, and then go to some other problem, try to apply new ideas. So he had this idea of this, what we now call Dyson spheres, where a civilization could build something so large that it will actually block part of the light from the star and radiate in the infrared. Right. So I think this was the first proposal of a technosignature that was not a radio signal. Right. And this is, to me, sort of this is sort of the things that we are trying to look for now. And it's really, to me, it's really amazing, and it's a testament to Freeman Dyson's vision, how we could start thinking in these terms in the 60s when everybody else was thinking about radio signals.
One of the things I remember hearing a while ago was this new project it's a budget with about $100 million called the Breakthrough Listen project. I'm guessing it's still going on. Are you aware of what the latest is with that?
Yes, it's currently the largest radio search that is being conducted. The history of SETI, and this is very interesting. We were talking earlier about Carl Sagan. He was one of the pioneers of SETI, and you mentioned the novel contact. It's amazing how a lot of the history of SETI is reflected in contact, and he even anticipated some of the things. What I mean is the following. When these radio searches started to become popular, NASA created a project to do these searches, on a large scale. And so NASA actually created two different projects. One of them was using the Arecibo dish in Puerto Rico, which was the largest and for a long time has been the largest radio telescope on Earth. And another project would be conducted using the deep space network antennas that they use to communicate with space probes in the California Mojave Desert. Now, this ran into trouble first in the 80s. There was a senator called Proxmire who tried to kill these projects because he thought it was a waste of money, tried to communicate with little green men. But and here this tells you how powerful Carl Sagan was at the time. He met with this senator and he was able to convince him otherwise. So he sort of saved these projects by NASA. And then later on in the early 90s, there was another senator called Richard Bryan who really shut down the whole thing down. And he did it. I talked to Jill Tarter once about this. We had an interview for my podcast. And she told us, well, something that is also known, but she said that she was surprised about how she thought there was something visceral, something very that he probably had some very strong emotional motivation behind this drive to not only shut down all SETI programs at NASA, but to do it in a way that it could not be rebuilt. So to trash everything. And most of it was rescued. It was picked up by the Planetary Society, where Carl Sagan was, and the SETI Institute that has been created recently. They picked up some of this and sort of continued doing on a much more modest, with more modest resources. So the radio search continued for a while, but in 1992, NASA stopped all involvement with this research. Some people think that there were probably religious motivations behind Senator Bryan's decision, but I guess we'll never know. And that's not so important, but what's important is that just as Sagan predicted in Contact, the government involvement with SETI was terminated, and then the search was picked up by private individuals, philanthropists, or some billionaires who had a profound interest in these issues, because this is something that we all share, right? So this is what happens in Contact, and this is also what happened in real life. In this case, we have this billionaire called Yuri Milner, who is I believe he's originally from Israel, or he has double nationality, American and Israeli nationality, and he's a physicist, if I'm not mistaken. And he's very interested in pushing not only SETI, but also some other sort of initiatives that are, that resonate with some of the deepest questions that we can have, but are still sort of at the frontiers of science. And the breakthrough initiatives are a collection of initiatives designed to push the boundaries of these fields. And Breakthrough Listen is the project to conduct a radio search. It's the largest project that we have right now. And as you mentioned, it's $100 million over 10 years. So it's only 10 million per year. If you think about it, it's relatively modest, and yet is the most powerful effort that we have conducted in SETI so far.
You're quite right. You highlight a very important aspect, the social and political aspect of doing this kind of research. I think that a lot of the scientists in the early 60s and maybe even into the 70s would keep well away from being associated with SETI because it was not seen to be scientifically sound and professionally respectable. But today, I think it's fair to say it is a valid research area. And good to hear that from what you're saying, the private individuals like Paul Allen and Yuri Milner investing in this. What intrigued me about your paper was the technosignatures. So from this point on, we're looking for signs of intelligent life, not listening for radio waves. So can you just summarize what a technosignature-based study for SETI how would that work?
Yes, basically technosignature, it's a denomination that has been introduced recently as an analogous to the biosignatures that we look or that we hope to look in the spectra of exoplanets. One of the things that has happened, it has revitalized the field of SETI, is the revolution of exoplanet science. It has changed astronomy. We have discovered now over 5,000 exoplanets confirmed, plus many more candidates. And we are starting to observe and characterize in detail these exoplanets. And we will soon start to characterize their atmospheres in detail. And this is going to be a breakthrough because the atmospheres tell you a lot about the possibilities of life in other planets. So this is now a big field in astronomy, is astrobiology and the search for biosignatures. This is not fringe science anymore. Looking for extraterrestrial life is not only respectable, it's one of the major drivers where lots of resources are being put. One of the drivers for the James Webb Space Telescope was astrobiology. So searching for life, not intelligence, life in the universe is now a main driver in astronomy, and lots of resources are being put into that. So we have these biosignatures, which are evidence that we can observe in an exoplanet that will tell us that there's life there. So some people thought that we could also look for technosignatures, which is something that will tell us that there is technology being used in an exoplanet, and that would point to intelligent life. Now, radio signals are a technosignature, of course, but it's far broader than that. We can try to look for other things. And people, when we talk about technosignatures, we can be talking about city lights. If we discover nighttime illumination in an exoplanet, for instance, that is of artificial origin, that will be a technosignature. We could look for industrial pollution in the atmosphere. If we find byproducts of combustion that could be pointing to industrial use, and that will be a technosignature. I don't know if that will be a desirable technosignature to find a lot of pollution in an atmosphere, but it will definitely indicate that there's someone there.
So we talk about the Great Wall of China that can be seen from space. So what you're talking about in technosignatures is some evidence of some civilization that's capable of building something that's so big on a planetary-wide scale that it can be detected from a very distant location. But the one that interests me really significantly, which is not something I had come across, is something called the Clark exobelt. Tell us what a Clark exobelt is.
Right. This is something I proposed back in 2018. That will be also something interesting to look for, is a large population of satellites surrounding a planet, especially satellites in the geostationary or geosynchronous orbits in general. And I refer to them using this Clark belt term. As you know, the Earth has a belt of geostationary satellites that we sometimes call the Clark belt. And this is a reference to Arthur C. Clarke, the famous science fiction writer. A lot of people don't know this, but he was not just a science fiction writer, but also a very I don't know how to say this. He didn't have a formal education, I think, but he had very deep, a very solid background in engineering and physics, and he was a visionary thinker, in my opinion, and he had lots of very, very interesting ideas. One of his ideas was the geostationary orbit. He was one of the first people to propose that there's a special orbit in which a satellite that you would put there will take exactly 24 hours in going around the Earth, and therefore it will be synchronized with the Earth rotation. And that means that it would always remain fixed on the sky. We would see it from the Earth's surface. It would appear to us as fixed in the sky at a particular location. And he already in the 40s realized that this will be a very interesting place to build a network of broadcast communication stations. And there's an article that he has in a popular magazine explaining this concept, and he does it with very solid engineering foundations. So because of that, this orbit is also known sometimes as the Clark orbit, and we have on Earth the Clark belt. So I thought that it would be fun to refer to exoplanets, extraterrestrial planets with a belt of satellites like this as Clark exobelts.
So what you're suggesting is that in the hunt for Earth-like planets around Earth-like stars, or sun-like stars, you would find these planets which would have these specific orbits, and every planet would have this. We've been using that orbit here on Earth for quite a few decades now. Given their current population density, be detectable from stars or other planetary systems right now?
No, not right now, at least with our technology. With our current technology, we would not be able to recognize a planet like Earth at interstellar distances.
Right.
That's the main problem that we have with technosignatures. Interstellar distances are so large. that we cannot see a lot of detail. So it almost requires a science fiction engineering to have something that we could observe from such distances. So there's always a bit of science fiction into this technosignature field. Now, when we talk about, so we need to look for superhuman technosignatures, because human technosignatures are not visible. When I mention industrial pollution, we will need to have superhuman pollution in a way, much more than we have now on Earth in order to be detectable at interstellar distances. When we talk about geostationary satellites, we need millions of times more satellites than we currently have in order to be able to detect them with our current technology. Now, what's interesting about satellites is that our population of satellites has been growing, and it's been growing exponentially. Okay, and in the past 6 decades or so, since we started putting satellites in orbit, we can observe that the population of this orbit, especially if you also consider the graveyard, because the satellites that we have in geostationary orbit, once they stop functioning, we push them into a slightly higher orbit that we call the graveyard, and there they remain forever, right? And we don't care about them anymore. But eventually, this graveyard will keep getting more and more populated. And perhaps, that's speculation, but it could happen. I think it's something reasonable to assume that eventually this belt will be thick enough that we could detect it at interstellar distances. Now, my estimate is that if you extrapolate current human population of this belt, we would reach detectability with current human technology in about 200 years from now. So there's always some extrapolation, but 200 years is not a lot. So this means that if we keep doing what we are doing, in 200 years, we would be easily detectable for people like ourselves from the nearby stars. And
so not just the population of the working geostationary satellites, but also the accumulation over time of the dead, non-serviceable communication satellites, which are pushed a little bit higher to make the critical space free for other newer usable satellites. So that density of the graveyard orbit would be detectable in your projections about 200 years from now. Matter of interest, we've one of the other things we talk about when we're talking about congested orbits is the potential for satellite collisions and the debris they generate, and the potential for the Kessler syndrome. So, could your approach work and detect a more denser, but perhaps filled with debris after multiple collisions of space debris that's populated and generated a lot of debris in a particular orbit? I guess it would be in principle the same thing.
Yes, actually, one of the criticisms that I received when I published that paper is that a lot of people suggested that it's not, that this could not happen, that the Clark belt could not get so populated because of the Kessler syndrome and other problems.
Right.
But I think we have to remember the Kessler syndrome refers to the low Earth population, the low Earth orbits, which is between 400 and 2,000 kilometers above the surface. The reason is that region of space is very, very crowded. That's where we have most of our satellites. But not only that, they're moving very fast because they're very close to Earth. The closer to Earth you are, the faster you're moving, and they're moving in random directions. So collisions take place at 10,000 kilometers per hour or more. Now, the geostationary orbit is different because it's much farther out. That means velocities are lower, and also it's a synchronous motion. So all the objects are moving synchronously, like a big procession.
I see. Right.
So relative velocities between them are much smaller.
Right.
You could have collisions, but it's much more unlikely, and it happens at smaller velocities. Now, said that, satellite collisions actually help the technosignature in the graveyard, because if you're an alien civilization or even ourselves, we don't care about what happens in the graveyard. If the satellites, if the graveyard is so populated that satellites start colliding, we don't care. They are dead satellites anyway. And these collisions, they actually increase the opacity. They make the belt easier to see because a satellite, which is a compact object, all of a sudden is spread out in a myriad of fragments. And the visibility of all these fragments is larger than the original satellite. So by smashing satellites and ripping them or destroying them into smaller fragments, you actually make the belt more visible from the distance.
Oh, so it'd be even more likely that these things will be detected. How close are we with the technology of the James Webb and indeed other larger Earth-based telescopes, which are either online or coming online soon? How close are we, do you think, of detecting some form of technosignatures in exoplanets?
Yeah, I think we are moving into a new era now, because for the first time with the James Webb and with the new large telescopes on the ground, like the ELT or the TMT, even the MGT in Chile, these new telescopes are so powerful that they would be able to detect human scale technosignatures at interstellar distances. The problem is that we first need to know where to look. For instance, there's a recent paper which suggests that with the James Webb telescope, we could detect human levels of industrial pollution in the Earth atmosphere in nearby exoplanets. But that will require hundreds of hours of observation with the James Webb. Now, so that means you cannot look at 1,000 planets and see what you get, because they are not going to give you hundreds of hours of observation without a good reason for that. And the same happens with ground-based telescopes. These telescopes are like microscopes. So they give you a lot of detail of a very tiny field of view. So you need first to identify a candidate. And that's what life is probably rare. I mean, rare. It's probably infrequent. I mean, only a small percentage of planets will have life, most likely, and intelligence will be even more rare. So you need to really get data about a very large number of planets in order to get a candidate. And I think that's what we are missing. How we can look at thousands of planets, or perhaps more, to identify one that is sufficiently interesting that we can then, pull out the big guns and go for it with everything that we have. That's the problem. How to identify a candidate? I think we still don't have an answer for that.
The Giant Magellan Telescope, the GMT, the European Extremely Large Telescope, the EELT, and the 30-meter telescope, TMT. 30-meter telescope. That just sounds astonishing. So I'm guessing within the next few years, some of these will come online. Yes, will you be involved in any of these projects specifically?
No, this is so competitive that, in fact, I don't believe that these projects will have a SETI observations program unless, like I said, there is some other clue or some other indication that will point out in a very strong way to a certain planet, because we have, these machines are so powerful that everyone wants to use them for other purposes. And right now, if we don't have a clear candidate, I think they will not be used for that. We first, like I said, we first have to identify a promising candidate first. And I don't quite know how to do this. And that's the sort of things I am trying to think about with these things such as Clark belts or, some other way that we can identify a candidate with more modest means that we can apply to a large number of targets.
Well, if anybody's going to identify a suitable target, I'm sure it's going to be you. You're quite right. It's a spectacular time to be doing this kind of research right now. But for the time being, so I'll come back and speak to you again then, but for the time being, Dr. Hector Socas Navarro, really appreciate your time. Thank you very much indeed.
Thank you for having me. It's been a pleasure.